of all the towns in Europe to hold a seminar, Cagliari is one of the most beautiful. And Daniele, who's an old friend, is a member of a very strong group of continental Europeans in industrial design, industrial experimentation. And we're very pleased to have him here. Daniele, is going to have a sequential methodology for integrating physical and computer experiments.
Thank you very much. I'm very glad to be here. I have to thank you, the organizers, for giving us so wonderful week. So it's amazing to be in Cambridge in front of you. This is a joint work with Alessandro Giovagnoli, who is here, and I must say it's still a very early stage of development. So we put forward the idea, and we hope we can discuss it. We'll be very glad to have instruction or guidelines from you on this topic. So let me introduce the problem. So I have this. So the problem is, imagine we are engineer, we want to improve a system or design a new system, and we want to do this by using together physical experiments and numerical experiments, simulation experiments. This is the problem. An assumption, important assumption, is that physical observations are more reliable, are closer to reality, but simulation costs less. So on this important information cost trade-off is based on the sequential procedure we are proposing. How can you approach this problem in a simple way? We can think it is a sequential experiment with two treatments in the fashion of clinical trials. So T0 is the physical experiment, T1 is the simulation experiment. We can imagine a sequence like that, which in the end comes to a stop. Of course, it's not so easy, like I'm saying now, because of course each one of these sequential experiments is an experiment by itself. So it's a sequential experiments of experiments. And we have to design each one of these experiments, which are different, run in different regions, different run size, and so on. Before going to the point, two questions. Is this problem relevant to application? I work in engineering faculty. I'm an engineer myself. I know for sure that this is a relevant problem. In industry, they use every day simulation runs and physical trials, but not in the form of structured experiments related to each other. This is the difference. Is this problem already being investigated? Yes, we have heard before about calibration of computer models. This is something which is similar but not the same, because we have different objectives. We want to optimize, we want to improve a system or design in the best way a physical system. And sometimes in that field, physical data are not designed. They take what they have. So there are these differences. Calibration could be a part of this method. So of course there are analogies with other statistical methods. For example, first of all, there is George Box sequential experimentation, but there is no simulation there, and the criteria to go on the sequential experimentation is only based on the expert judgment. Also, sample service is a field of interest, because there is information which can be taken directly or by proxy, and an important problem is how to allocate resources, runs on the two wave of investigation. Of course, there is no sequential approach there. Computer models with different level of accuracy, we have seen the first presentation today, but it's only computer there. Sequential clinical trials I've already mentioned. So before going into again the formulation, just a couple of experiments related to engineering problems which I've dealt with in some some years ago, and the last one was very recent. Here, I try to apply this method of alternating physical computer experiments, but basing on my judgment. So the novelty with respect to what I'm showing now is that we have an automated structure that decides how to go on. This is a climbing robot, a robot which is supposed to climb on posts or trees or cables or bridges in order to operate in risky operation, in hazardous environment and something like that. So this is the lab setup. This is the robot in the lab. We have developed a simulation model and working model, which is a known program for mechanical design. We have investigated 21 factors. So this is the overall structure of the investigation. On the right, we see physical experiments and the computer experiments. Physical experiments were quite limited because they cost a lot, just 28 run total, while on the other side we have more than 200. We start with extensive exploration on the computer, and then we can build at that time the prototype. We had guidelines to build a prototype. On the paper we had a feasibility check on the prototype, and then exploration of the feasible region, which was slightly different from this. And then the confirmation of the good results on the physical experiment, by the physical experiment, and then since the results were not confirmed in the best way here, we could find, the engineers could find the way to modify the code to improve the simulation model in order to get closer approximation to the reality. And then, after having done that, we optimize having confirmation. I'm not used to this. There are a lot of benefits here coming from the conjoint use of the two investigations. In the end, the design was wonderful in the sense that the robot can climb steadily with a speed which is 7 times more than the initial design solution, and virtually on any post surface. So it is robust with respect to the change of the friction between the rings and the post. We just built one physical prototype. Without the simulation, we should have been built hundreds or at least tens of prototypes. Computer exploration gave us the opportunity to find a situation of innovation in the robot, which was not in the expectation of the designer. We see here that we could be able to find that the robot can fall in control passively by its weight, thanks to Newton. Yeah, this was a side effect, very beneficial. And then we patented the thing. So the merit of the conjoint use are quite a lot. This is the second application I will describe very briefly. This is a process, a manufacturing process, flocking process, which is intended to produce flock yarns. Oh, sorry, this one. Flock yarns are then woven and used in automotive industry as a cover for components in car interiors, or, for example, also the seats. Maybe you know the velvet-like fabric used in the car. The process works. Sorry. There is an array of threads coated with glue passing through a chamber where there is an electric field, and the electric field push upward this, which seems a powder, but they are little tiny particles of polyamide, and this particle goes up and hit the threads and stay there. So this is the process. We developed two simulations model here, one for the electric field inside the chamber here, and one for the motion of the flock. Again, thanks to Newton for the motion law. We investigated 9 factors. This is the structure of the investigation again, the same fashion as before. Here we have the possibility to have more physical RAM because we have the production line, we have a pilot plant in the company where we do this project. And so the runs are 90 here, physical runs, and simulation runs a bit more on the 2 simulator. This is just the first simulator. This is the integrated simulator. We developed this simulator in MATLAB, the simulator of the flock motion. So a lot of benefits came also here. We could be able to enhance a lot process efficiency. So the number of little particles attaching to the thread in the unit time was increased a lot. And we can use this efficiency for 2 reasons. First, for process improvement, we can go faster, so raising productivity. Second, for imagining new products, new application of the technology. Okay, so this is a way for product innovation again. We did computer model calibration because there were parameters to tune, physical parameters to tune in the simulators. And also, we could be able to build a mechanistic model of the process, combining results from the one particular important physical experiment and data from simulators. This is a very quick to use process design tool because if they want to test different operating conditions than they are using at the moment, they can. This is an analytical problem, model, sorry. Okay, so this is the formulation. It's a very simple level because, as I said, this is the start of the research. So imagine this is the unknown reality. Physical trials are modeled by reality plus an error with standard hypothesis on the error. Simulation is reality plus systematic deviation, which is this bias. The domain is an hyperrectangle, so very simple. And the physical response and simulation response are, for us, response surfaces which we can estimate by polynomial regression over the region of interest. We estimate the bias function by the difference of the predicted model for the simulation response and the physical response, which is the objective, the general objective of this. We want to locate in the domain a sufficiently high value of the true response over the domain by using simulation as much as possible because it's less expensive, provided simulation is found, constantly found reliable enough. So for users, it's very important to optimize the system if they have a simulator and also possibility to a physical setup where to experiment. But not only that. If they have a simulator, it's important to know if the simulator is worthwhile to use. Otherwise, they waste time. And this is typical. Everybody has a simulator. Everybody uses it. But nobody is sure if this is correct to be done. So there are 2 objectives there. The sequential procedure is quite simple. At each step of the procedure, we must decide what? The type of experiment, if it is physical or numerical, and this is the high-level decision. And then we have the low-level decision about the region where the experiment is to be run inside the domain, the run size, and we have to find the design in that region. We make simple choice throughout. The region is an hypercube of fixed size with center CK, and the design is a Latin hypercube. Which is the rationale of the procedure? We want to use physical experiment only in 2 particular situations. So we want to use simulation experiments all the time, So it's easier to define where we don't use simulation experiment. We don't use simulation experiment so we use physical experiment. In this situation, we have a satisfactory response level found in simulation, and then it's worth checking it on the physical system. Or we have suspicion that the simulation is so unreliable that maybe it's not where to go on with the experiment. So we could possibly stop in there. A physical experiment is used as a checkpoint of results I obtained by simulation. So a physical experiment is always run in a region of the preceding simulation experiment, just for confirming or not what I've found in simulation. So Rk is equal Rk minus 1 when I have a physical experiment. When we want to stop the procedure, this point 1 is related to this point 2 to this. I found a good solution in the simulation. I found that this solution is confirmed in the physical setup, so this is a success. I stop it. In the other case, I have had suspects about unreliability of the simulator. I have to confirm that the simulator is too unreliable, so I stop the experiment. This is not a termination which we can consider unsuccessful. As I told you before, it's important to know that simulation is rubbish. Which are the allowed transition here? We make this choice. The start is fixed. We start with the simulation experiment, and then we have, as soon as possible, a measure or reliability of the simulation experiment. So we need a physical experiment as a second step. If we are in a simulation experiment, we can go to another simulation experiment or to a physical experiment. So we can never go to stop the procedure. If we are in a physical experiment, we can come back to a simulation experiment or stop. We never can have two consecutive physical experiments, given our assumption. We need performance measure at each stage, because, of course, we have to build the traffic light of this procedure. Measure satisfaction, which is the maximum value of the predictive model of the response in that region. Incremental satisfaction with respect to the last experiment of the same kind is the difference of two values of the satisfaction function. The expected improvement in next simulation experiment. This is important to locate next region. It's very simple. This function is the maximum of the modulus of the gradient vector on the frontier. Of course, the gradient vector must be going out the region. So the gradient indicates the direction of maximum increase of the response. So the most desirable region where to experiment more in the simulation. Then we have total cost at stage k. And finally, the most important function, which is the measure of the unreliability of the simulation. There are two definitions. The most important is the first, because it's the direct measure, because at a step where a physical experiment is done, since the previous experiment was simulated in the same region, in that region we can have a fairly good comparison. So again, here we have the square bias compared with the error variance on average integrating over the region. This measure can be updated even in other steps where I don't have the couple of two complementary experiments. This is just an average of the measure in the region where I have the couple of experiments, penalized by the distance between the center of the new region and the center where there is this fair comparison. So this is, I would say, an estimated measure of unreliability where I don't have the direct comparison of the two. Finally, our transition rule is quite simple. This transition is important when I stop simulating and go to physical, when I am satisfied enough of the value I've attained in simulation, or when I'm not satisfied about the reliability of the simulator. Otherwise, I go on simulating. Here, this transition is important. When I stop in two situations mainly. These two are the most important. Satisfaction is high and it's being confirmed by a physical experiment, or simulation is too unreliable. Better stopping, thinking about improving the simulation model, and then start with another procedure. If these two rules never trigger, it's useful to introduce something to stop the process. So it's better to verify if I don't have any actual improvement. Actual means physically confirmed. Too many stages without actual improvement, I can stop, or I stop when money is finished. Okay, this is just an overall look of the procedure I've described. These blocks are big block, so there is something inside, of course. What is inside? I have to select the region, next region, the run size, the design, run the experiment, estimate the response, and compute all the performance measures I've defined. Low-level decisions, which is how is selected the region, next region. Of course, if the experiment is physical, the region is the same as the previous one. There is no to decide, nothing to decide. When the simulation is simulated, the experiment is simulated, the region is different. So if there is a direction of improvement or increase of a response outside the region, I choose the region to be adjacent to the previous. So I have a formula to compute the center, which of course says us that the center is in the direction of the maximum modulus of the gradient, or the gradient where the modulus maximum, here, for example. Here, this is the center is in the direction, and the constraint is that region are adjacent. You see that the size of the experimental region has been taken fixed. What changes is the run size inside this fixed size region. If not, if there is no, this is not greater than 0, so I draw the new region at random. I throw the dice and see if something better will come. Okay, run size. The first principle is a balance of cost. If I spend some money for a simulation experiment, I want to spend the same money for the next physical experiment run in the same region. So this is the choice. If rho is the ratio of the cost, which is between 0 and 1 because simulation costs less, I choose run size, you see, for the physical experiment in this way. For simulation experiment, I make the run size proportional to the expected improvement in the next region. So if I have more expectance of improvement, I spend more. I can calibrate this by setting which is the willingness to pay for obtaining improvement, delta y. When the region is drawn at random, we put again the run size equal to the first run size when we didn't know nothing about the problem. So this is, you will see a different run size. Here the modulus is larger, I have more point. Here the modulus is smaller, less point. So, one demonstrative case. I have implemented a computer code for running this procedure in a complete automated way in MATLAB. And this is the case. Green is reality and blue is simulation. What we see here, we see that there is a lot of discrepancy here, a lot of discrepancy here. So there is just a region where agreement is acceptable. So we want to be aware of that. We want to notice this unreliability of the simulator. So this is one trial of the whole procedure. So this is the starting region around 0. This is the size of the region. The second experiment is physical, is the red one in the same region. There is discrepancies, but is not over the threshold, so it's acceptable for now. And then so we continue with in simulation. These are the points. This is prediction. We continue because there is improvement here, expected improvement. The derivative is positive. In this region, in the extremes, there is no expected improvement. We are going down both sides. So we draw at random the center next region. The center comes here. So this is the simulation. Then this number is good, very high, fairly high. It's worthwhile to see if a physical experiment confirms that. Physical experiment doesn't confirm that, so the procedure stops. S1, P2, S3, S4, P4, stop, P5, stop. Another case, just the same setting. The only thing that's changed is the size of the region is 3. Before was 2. So again, simulation experiment, physical experiment, and then here there is improvement. So simulation experiment, I can reach a value over the threshold which was 10. So I had to run a physical experiment here, and unreliability is not so high. So I accept the solution and stop. If I have 1 minute more, I can show you these two cases. Here, simulation, oh, plenty of time. I was too worried. Simulation is equal reality. So what happened here? I should find the maximum here, or at least a level which is up over the threshold. First experiment, second experiment, and third experiment. There is no improvement here, so randomly I jump here. I find a good situation over the threshold. So confirmation by physical experiment. Unreliability is low, so okay, I stop here. This is the maximum. If you go back, this one. Oops, sorry. Reality is here. This one, the green. And the last case, always simulation equal reality. We start here. This is the usual start. Then here we jump here. There is increase here at the border, so I run another simulation experiment here. There is no increase possible, so I jump again here. I found the maximum. Okay, so it seemed to work, but it's just initial tentative. The software is there. We have to do a lot of experiments on the software. So just to summarize, the scope of this approach is wide in general, because we can deal with any situation where the response can be measured by two instruments realizing a different quality cost trade-off. So there is space for extensions. The method now is aimed at performance optimization, in a sense maximization of a distance measure in the output space, but we can have different goals. For example, we can maximize a distance in the input space if we want the design solution to be very different from the initial one in terms of input factors. Or we can maximize a distance measure in a space function where we can express the relationship between the y and the x. So this could be a way to, this could be a way to express the broad concept of innovation, which is much relevant today in industry. We need a lot of testing. And then there is the last thing which concerns me, and this is the comment on George Box in his book. He said the reader should notice the degree to which informed human judgment decided final outcome. So I know human judgment is important. I know that human judgment is in the procedure we have developed, but still there is this question. You have the answer? Shall we ask it? Thank you very much.
Challenging questions.
I understand that your simulator stays the same through this whole process.
Yeah.
But it seems to me if you're doing this and you're collecting data, you might want to be improving your simulator during the process. So you might want to go back and reanalyze the original data with the better simulator as you go through. Have you thought of that as a
No,
way?
no, the simulator, yeah. You understand what? The simulator is one, and I use it in different regions, never in the same. I don't come back in the same.
Yeah, but if you improved it, if you had an improvement of the simulator during your experimental process,
In the sense, I modify
Yeah.
the code.
you modify the code because you've learned by comparison with the physical experiments that
Yeah, yes, this was my intention, but Sandra, there's nothing to hide. Sandra, in the end, I agreed with her. Sandra said, that if we modify the code, this is another procedure. In the end, she convinced me. I would have put this step, but this is not easy to automate. So we have to stop, change the simulator, and then go on. Yeah.
Other question. Can I ask one about robust design? I mean, it had a flavour of robust design. In fact, you mentioned robustness at one point.
Yeah.
Have you got stochastic robustness criteria in there, like finding the maximum but with minimum?
No, not yet.
But the
Of
plan
course,
is to.
it has to be improved a lot, especially when we confront with application. This is the field where we can understand if it works or not.
Other suggestions? What about the question here? Judgment or automation? Anybody, Dan, or anybody with experience?
It's a question.
A question, not a solution. Ask a question.
In choosing the region for the next simulation, it sounds a bit like extrapolation. How do you choose that?
Because if you want to improve, you have to have some indicator, and the gradient is what we have. I know it's on the border of the region where we experimented. Yes, we could have other choices. I don't know. We could do
The size of the regions, but here, is that something that has to be decided as well? Do you
Yeah, we tried to, but it was getting too complicated. So we decided to keep one thing fixed and change the run size. But of course, this is a seminal stage where many things can be fixed in a better way.
Can I ask one quick one that I'm just with a whole motor car? You put it all together essentially by simulation. Then you road test it. So, I mean, the situation is very, very serious when you get very big systems because both cases, the computer, the experiments are very expensive. Road testing a car is extremely expensive, or wind tunnel for an aeroplane.
Yeah, this is one of the two objectives, to understand at early stage if the simulator is good.
All right, well, thank you very much, and thank all the speakers, a wonderful session.